Okay. Let's start with RDD and with this paper that evaluates the impact of cohesion policy transfers by considering two specific fields of intervention that are research and innovation and transport accessibility. I will go very quick. So the paper focuses on the effectiveness of cohesion policy, considering the programming period 2000-2006, and looks at research and innovation activities and potential road accessibility. It uses regression discontinuity design, both considering a parametric and non-parametric approach. For those of you that don't know what is the EU regional policy, which is aimed at reducing disparities between the level of development of the regions and the backwardness of the least developed regions. In the programming period 2000-2006, the priorities of the policy were fixed by three objectives. Objective 1, which were the least developed regions, then that became then convergence regions in the subsequent programming period. Objective 2 and Objective 3. So the Objective 1 of the EU regional policy aims at promoting the development and structural adaptation of the lagging developed regions, and the aids is devoted only to regions that have a per capita GDP lower than the 75% community threshold, as we were mentioning in our example this morning. During the programming period year examined, research and innovation and transport were two of the major fields of intervention of the policy. So as you probably know, the literature assessing the effectiveness of the EU cohesion policy is quite vast, and there are more than 50 studies that were using different techniques and also got to heterogeneous results. And most recently, this policy has been evaluated by using a quasi-experimental framework and relying on RDD type of analysis, which is in line with this study. So in this analysis, the forcing variable is the regional GDP per capita. The cutoff point is the 75% threshold, and treatment is the eligibility to the Objective 1 fund. The analysis is carried out, as I said before, using both parametric and non-parametric techniques. We will consider first non-parametric estimation that use local linear regression and based on different kernels and different bandwidths. And as a robustness check, we conduct a McCreary test to assess the density function of the forcing variable and exclude manipulation. We look at the absence of jumps in the levels of the treatment and of the outcome, and absence of discontinuity in other covariates that should be not affected by the treatment. Then we also conduct an OLS regression to see if results are in line with what we obtain in the non-parametric way. The data used come from a data set of DG Regio, and we selected two specific fields of intervention, and we consider two specific outcomes for each field of intervention, in particular patent application for research and innovation and potential road accessibility for transport infrastructure. So here I describe a bit the cleaning of the sample, because there were some units that were non-objective 1 but still were receiving funding. There were units excluded because they represent outliers, as they are, for instance, the République d'Outre-mer for France and so on. We also conducted analysis on different periods and subsamples for sensitivity. I will skip the descriptive statistics, so we gain a bit of time, and the results are pointing to a positive effect of the policy on patent application, and a first evidence of the regression discontinuity design is given by a graphical analysis. Here with the visual inspection, you see that treated units that are the red dots have a slightly higher level of patent application than control units that are the blue dots. So this is a first naive estimation of the effect. These are the results. This is the output, more or less, that you obtain when you run regression discontinuity design, in which we are considering different bandwidths, the optimal, its half, and its double. And then for different kernels, this is estimated in a non-parametric way. And you see that with Gaussian and a Panechnikov kernel, you obtain a positive effect of the policy. These are the different sensitivity analyses considering different subperiods. And finally, here we have the parametric estimation, in which we replicate the analysis that we did in the non-parametric way, but using different parametric regression with different polynomial up to the third order. So we have a linear regression, a quadratic function, and then polynomial of order 3. And here we look at how the discontinuity varies according to the kernel and the different bandwidths used. So it's still sensitivity of the analysis, and this is the result of the McCreary test, in which you see that differences between the two sides of the distribution in the two sides of the cutoff is not statistically different. The same analysis, I will not go into the details because the presentation of the paper is not our goal, is run also for the potential road accessibility. So in this data session, this paper was written in 2014, more or less, published in 2017. So uses SATA packages that are now been replaced by RD Robust. I will first show you, because I think that starting from the simple way is also useful for you to understand. I will first start from this simple analysis with the older packages to let you practice a bit with RDD, and then I will show you how the new RD Robust SATA package works. Okay, so if you open the folder that I shared with you, there is a zipped folder which is called Student A. So unzip the folder and maybe put it on your desktop or your C drive. And I will do the same. So is upload 1. The installation of the module for the McCreary test is a bit tricky because there is no SATA packages, and so you need to create the ADU file by yourself. But you have the instruction. So if you open student A, you have a data set which is called mask dataset, and then Ferrara underscore sh, which is your do file. This do file is incomplete. First of all, you have to install all the requested packages. This is based on Stata 14, so I don't know if it works now. It works on my laptop, but I don't know if it works on yours. And you also find here in the commented text the instruction to install the McCreary DC density ADU package that you also find in the folder is DC density. Okay. So first of all, you should set your working directory. So you copy your path. Have you installed all the packages? No, they are all here. But you have the do file. Yeah. So you see, install the programs you need. It's difficult to read here. Yeah. Yeah. But it's in the do file. If you open Ferrara underscore sh, you have the same. You install the packages. Okay. Yeah, the most tricky is DC density. But you can skip it by now. Okay. So first of all, we need to generate variables and labeling. First of all, you should generate a dummy, objective 1, which is based, which is equal to 1 for the treated regions. So it identifies the eligibility. And then there is a hint. It is based on the variable eligibility 9406. So you should generate double objective 1, which is equal to eligibility 9406 equal to treated regions. So this is your treatment variable. Then we should generate our forcing variable, that we call X, which is the GDP per capita score, right? So X is equal to GDP underscore PC PPS 8890 average. You have it already. And then you generate its square term, the triple, and the interaction with the dummy. These variables are useful for the parametric estimation when we are considering different polynomial orders. In this exercise, we focus on the restricted sample of patent application. So the outcome variable Y is the growth of patent application over the period 1999-2010. The forcing variable is this indicator based on per capita GDP. The cutoff point C is 75. Then the treated group is identified by the eligibility for objective 1. As a first intuition about the existence of a discontinuity is given by the graphical inspection. So here you plot a linear polynomial fit with the confidence intervals for the treated and for the controls. No, I have not created anything. Okay, so here you have if treated, so you should substitute treated and not treated with the condition that in your sample identifies being treated or not treated. So we said that treatment is identified by the dummy objective 1. So you will have L poly CI, which is your outcome. Is this. So your outcome is the growth of patent application over the period 1999-2010, okay? So you should replace Y with this variable if you want to do it by yourself. Otherwise, you can look in at the folder upload to, where you find an already compiled do file, okay? So we consider growth of patent application 1999-2010, then this GDP indicator, which is the forcing variable, and we plot the line over time of this variable for the group of treated, which is identified by those objective 1, those regions eligible for the objective 1, and for the controls. Then we also plot on the same graph a scatter plot with the same condition. The result is this. So we have the local polynomial of for the objective 1, the local polynomial fit for the non-objective one, the confidence intervals, which are identified by the gray shaded area, and the cross and the dot that identify the units are the scatter plot. Here already we observe that on the left-hand side of the cutoff, we have a higher growth in patent application compared to the right-hand side. So we could say that this naive inspection of the discontinuity suggests that units, regions eligible for the objective one experienced a higher growth in patent application compared to units not eligible. Okay. Another way to have a flavor of the existence of the discontinuity, not considering the bandwidth, is to simply regress the outcome variable over the treatment variable. And you see that in this simple regression, we observe a positive and statistically significant coefficient, suggesting that on average, objective one regions experienced a higher growth in patent application compared to non-objective one. Then let's apply the RDD estimate. So as I said, this do file is built by referring to the older version of the package, which is RD. That stands for regression discontinuity, in which you regress. You first of all set the bootstrap replication to have a better and more refined estimates of the standard errors. Then you have RD, which is the command. I set them to 100, otherwise it took too long. This is the outcome variable. This is the forcing variable. And then you set the bandwidth. The bandwidth is computed by default by this package using a statistical procedure developed by Imbense and Kalyana-Raman. And by stating 150 and 200, we are asking Stata to compute the effect by considering the optimal bandwidth, which is 100, its half, and its double. And Z0 is your cutoff point. And then you can choose between different kernels. So we have triangular, Gaussian, rectangular, and Epanechnikov. Let's see what happens with the Gaussian. This is the result. So with the optimal bandwidth, we obtain a positive effect for the objective one. Then you have the half of the bandwidth and the double. You can also consider the other kernel for robustness. You may also have information about the optimal bandwidth. If you ask, if you look in the e-return list of locals, you see that the optimal bandwidth is 22.8, meaning that the software has estimated the effect by looking at 75 plus 22 is 97, and 75 minus 22, which is 53. So we are considering in our analysis regions that have a forcing variable included in the interval 53-97. Then so this means that non-objective one regions are experiencing a growth which is lower of 1.06 percentage points, I think it is, compared to objective one. This is at the optimal bandwidth. Then for robustness, you might show the results for its half and its double. And you see, if I consider half of the bandwidth, you see that the results is still there in magnitude, more or less it's the same, but it's not statistically significant. This means that if you look very close to the cutoff, you lose statistical power, but this is due to the fact that you might have few information close to the cutoff point, because we are talking about regions, so we don't have so many observations. And then if you enlarge the bandwidth, what you get that the effect in magnitude is higher. But this could be due also to the fact that since you are going more far away from the bandwidth, from the cutoff, you might be considering regions that are quite different one to the other. Okay, so then you do a bit of sensitivity using different kernels, different bandwidths. Then you have to show the McCreary test to demonstrate that there is no manipulation. No, it's not the McCreary test. You are showing how the discontinuity varies according to the different bandwidth you use. So basically you are plotting what we saw in the table, whereas the McCreary test is here. And you show how is the distribution of the density function. So this is the density function of your forcing variable. DC density, your forcing variable. The breakpoint is 75. And here you show how this varies on the two sides of the cutoff. So you see you have some outliers here. You have some units that are on the tail, both on this side and on the other. Then as a robustness, you might also want to estimate some parametric models in which you introduce, you regress the outcome on the forcing variable, you regress the outcome on the treatment, or you regress the outcome on the forcing variable and on the treatment. Here, oops, sorry. For instance, you see that objective one have a higher growth rate compared to non-objective one, and you might discuss a bit on the interaction. And this is the simplified do file. If you look, but we we will not consider it together. If you look in upload 3, I think, let me check, you will have upload 1, upload 3. No, in upload 2, you also have the edu file, which is called Ferrara, which is the full replication do file of the paper, in which you create all the tables, and you also have the robustness, including other threshold and so on. Now let's look to upload 3. In which you have RD Robust illustration. So RD Robust is currently the most widely used startup package to implement regression discontinuity design analysis, which has been developed by Calonico, Cattaneo, Farrell, and TQNIC. They have a very comprehensive data website on regression discontinuity, in which they provide all their papers and book chapters on regression discontinuity estimation, plus packages for Stata and for R. So if you have to carry out regression discontinuity analysis, I would suggest to go to their to this web page, which is a Google site, and have a look to what is most of interest for you. So in this case, what we were doing before manually is implemented in a single command and in the option provided by this single command. I will show you some features. So it has already a command which is rdplot. That, as you see, provides the visual inspection of the evolution of the outcome for treated and controls, and it also allows to have beams of the observation to plot the confidence intervals and so on. And for this you have also several options regarding, for instance, how beams are defined and how variance is computed. Let's look at RD Robust. RD Robust is the main command that performs the RDD analysis. You see, in this case, we used the default bandwidth computation. So the optimal bandwidth is already estimated by the program, and we are using a triangular kernel. And you have also information about the number of observations that you have on the left-hand side of the cutoff and on the right-hand side. The polynomial order used, which is the bandwidth. You see here the bandwidth is 17.75 on both sides. And these are the estimates. It also provides robust standard error. And the help file of this startup package is quite detailed, so you might look more in deep to the specific features. This package allows also to estimate asymmetrical bandwidth. But then it depends. I think that when you use asymmetrical bandwidth, then you should motivate why it should be different. Because the package does everything data-driven, but maybe then it's not meaningful. No. No, you won't get, you will lose in terms of statistical significance. You can use RD plot also to show RD robust estimate. So instead of showing the table, you show the graph. In this case, it's a linear function. Then this in the second version, in the revised version of this package, you are also allowed to introduce covariates. At the beginning, it was common to avoid the use of covariates in RTD because this seems counterintuitive compared to the approach used by the method, because the method is based on the assumption that the units on both sides, very close to the cutoff, are similar in all respects except the treatment. So if this assumption is valid and you are applying this method, you don't need covariates. However, they introduced the possibility to have covariate in the command. So you can also account for observable differences for your units. And this is the case. But it's not always true that covariates improve the estimate. And in this do file, you will have a case in which they add population, which does not improve the performance of the estimate. You can also use different clustering methods of the standard error. And here, you can use different we are using different bandwidth. You see, in this case, you have a bandwidth of 14.6.7 on the left and 20.99 on the right. So this is a case in which they are using asymmetric bandwidth. If you want to decide by yourself which is the best bandwidth, you can use the command rdbw select, in which you have the different method. You see how many methods they use for bandwidth estimation. And you might also set manually which should be the bandwidth to use for your analysis. Okay. Now I will briefly show some other extension of this set of commands, all provided by the same authors or a subset of these authors. So in this case, we have the command RD density that is analog to the McCreary test, even if this is a slightly different test, but it is aimed at assessing the absence of manipulation around the cutoff. So again, you see if there is evidence of a jump here. Then they also do a placebo test on predetermined covariates. That is one of the robustness tests that I mentioned before. So you should not find any effect on covariates that are not supposed to be affected by the treatment. You see that in this case, there is no jump at the cutoff point. Then, okay. Then it also has a package to do randomization inference, but it took a lot of time, so we could not see it. And there is a book chapter that explains how does it work. This is RD power, which is useful because it's given that we are using non-parametric estimates. It is difficult to motivate which one is the best model we decide to select to estimate our impact. And sometimes a reviewer or someone interested in the analysis might ask you to provide evidence to support your choice. RD power goes in this direction and allows you to estimate the statistical power of your analysis conducted with RD robust in order to identify the best model. That's what in the past we were doing when using the R square to identify the statistical information power of an OLS, or what we were doing with the HAIC, the archaic information criterion, or the BIC. In this case, it is estimated after the RD robust. Finally, which is quite a nice advancement for RDD analysis, we have RDD multi, I think it's called. That is important because it allows you to conduct an RDD analysis when you have multiple cutoff or multiple scoring. So you might have multiple non-cumulative cutoff. So for instance, I have a cutoff at the age of 25 and I have a cutoff at the age of 30. Then it allows to conduct the standard RDD analysis and graphs on these. You might have multiple cumulative cutoff. And you might also have different scoring process. So imagine in the scoring of schools, you have a different scoring with different cutoff for each school. The nice thing is that this command provides you also with a plot. Let's see. This one. Which highlights the effect for each cutoff. It's here. No. So in this case, you have two different threshold, 1 year and 1 year. And you see how is the jump represented in proximity of each of these cutoff.
And then we assume that all three are similar.
You assume that these are similar to this, these are similar to this. So in proximity of each of the cutoff, treated and controls are similar. Okay. And so this is it for the RDD.